So we are now at the last of our chapters of our, I don't mean our intellectual life, but our dialogue.
Yes.
And as you said just before we started this last session, you said, oh, maybe this dialogue is not so infinite after all.
Well, the ideas have a future. There are still many questions to resolve, but this is as far as our discussion goes.
But you know, you were saying yesterday, off record actually, and you were a bit saying that at the beginning of our different sessions, that you felt that you didn't have enough to say, that you do have enough to say. And I was telling you that I don't agree, but that in fact, this feeling of incompleteness, what makes you infinite, because it refers to the fact that, of course, your awareness of the infinite makes you feel that you haven't said everything and you can't say everything. You can't say everything. You don't feel complete, and that's what makes us human. And it's our window to the infinite, I think. That's one of the main thing. That's the reason why in this last session we are going mainly to talk about what's the point of the infinite, because we have talked about that for so long. Is there a relation between the infinite and transcendence, something that goes beyond us, that might be part of us, but that goes beyond us? But before that, we were talking yesterday about two things, and you wanted to add some comments. You wanted to add some comments about those two things, and it might be related with our last session, actually. The first one was about the idea of discrete particles, how they are related to each other, and the second one, it was about quantum computing. So maybe you can talk about the first one.
The quantum computing topic is easier. I view Turing's 1936 paper that imagines the computer as a mathematical idea as actually a very deep physics paper, because it's positing what can be calculated in this universe. So it has deep consequences in physics, it seems to me. It already suggests that there really are not real numbers in the physical universe, because if there were, one could have a computer computing with infinite precision real numbers. And the Turing machine, if you say that that's what computation is, then that's not possible, because a Turing machine cannot deal with infinite precision, an infinite amount of information, only a finite amount of information. Well, anyway, quantum computers sound like they may refute Turing's definition of a computation, because there are quantum computers, at least in theory. In practice, we don't really have it as a practical technology. But
not yet.
Right. I'm a little skeptical, but anyway, not yet, definitely. So what happens? The quantum computer cannot calculate anything that a Turing machine cannot calculate. It's just faster. It can't do computations that a Turing machine can't. It cannot do computations that a Turing machine can't do. So what can be computed stays the same. The only difference is that quantum computers are faster at some things because of something called quantum parallelism, exactly, which is the superposition of many computational paths. Right. Yeah. And actually that is...
using quantum superposition.
Right. But actually there's a nice name for that. It's actually the idea of quantum computers is the idea of the Feynman path integral, which is one of the ways of formulating quantum mechanics, which says you take a sum over all possible histories. So a physical system, in some sense, can be, its behavior can be represented via Feynman path integral, which is a sum over all the possible time trajectories, all the possible histories of the physical system, combined in a certain way according to a formula that Feynman wrote down. So that's, again, this idea of quantum parallelism, right? Doing many computations at the same time. Now, I forgot my own best arguments yesterday about why I would like the universe to be discrete, the physical universe. The mathematical universe is discrete because mathematical theories are like computations. A formal mathematical theory, a logical system, there's a proof-checking algorithm. And the size of that algorithm in bits, it's a computer program, is how I measure the complexity of a mathematical theory. And that's an important number which tells us a lot of things about what a mathematical theory can do or not do. Now, I would like to apply the same methods to physical theories that work so well with mathematical theories. But that doesn't work if the physical universe has real infinite precision numbers. It only works if the physical universe is discrete. In that case, I can model a physics theory as again, a computer program that calculates the experimental data, which is assumed to be discrete information. Mm-hmm. And the best theory is the most concise program, and the size in bits of that program tells you important things about the physical phenomenon. That's the size in bits of the most concise theory for something. So then you're doing an analogous analysis of the scientific method and of mathematics. And the name I give to this is thinking of epistemology as information theory. It's a version of epistemology based on algorithmic information, looking at the size of computer programs. And it works better if the physical universe is also discrete. So that is my model. I would like the physical universe to be discrete because it makes epistemology, my version of epistemology based on information theory, work better. Now, are there any arguments from physics in favor of a discrete universe? Well, sure. I used to have a colleague at IBM, the physicist Rolf Landauer, and very often when I would bump into him in the hallways, it's a very big building, he would say, oh, information is physical. And another thing he would tell me is no physical quantity was ever measured with more, I don't remember, it was 13 or 16 digits. It was less than 20 digits, So that's as far as you can get, actually. There's no such thing as 3.141596 forever in the physical world. Nothing can be measured with infinite precision. It doesn't even have any meaning. So another argument for a discrete physics comes from the thermodynamics of black holes. I don't know if this is still popular among physicists, if it's still accepted. But years ago, I read a book by Lee Smolin called something like Three Roads to Quantum Gravity. And he discusses something called having to do with black holes, the thermodynamics of black holes. Something called the Bekenstein bound and something called the holographic principle. And basically, this is an argument which says, well, it starts originally from black holes and information on the event horizon. But you then extend it to any physical system. And what this argument says is that any physical system can only have a finite number of bits of information. These are classical bits because gravity is a classical theory. Nobody actually has managed to unify quantum mechanics and the theory of gravity. And some people are even proposing now that one shouldn't try, that gravity is saying something. It's saying it wants to be classical. So these are classical bits. Any physical system, according to this argument, which I don't know if it still finds favor with the physics community or a part of it, says that a physical system can only have a finite number of bits of information that grows not as the volume of the system, which is what you might expect, but it grows as the surface. And that's why it's called the holographic principle, because in a sense, it looks like all the information inside the system is projected onto the surface. Anyway, I don't know if these are esoteric arguments dealing with black holes, which are objects you don't have in the lab.
Yeah.
So it's all up in the air. I don't know if this theory...
Yeah, but what I hear in what you're saying is one thing, and another thing that I will come back later, it's about quantum computers. But one of the first things that I hear is that if what we call reality is irreducibly, discrete,
Non-discrete. Mm-hmm.
it becomes also irreducibly non-computable. To try to summarize what you have said. So I will say that in a way, isn't it this, like you will say, like something with the psychological mathematician mind that wants to see the world in discrete quantities and transform it, even when they are dealing with computers, into bits of information, like the equivalent in the computing world of discrete particles in the pure physical world, to say all that works, and so we can make very easily our calculations. And if we do that, oh, that's good, because we don't feel, as we said the other days, we don't feel the danger. And maybe you don't want to feel the danger. You don't want to feel the cliff, like the cliff of the, I will say, a universe that is non-discrete, so that you can't actually put into those little boxes that you call particles, and all those little boxes that you call bits in computing in computing. In computing science. I'm wondering if there is not some kind of a psychological bias here, like refusal of this irreducible feature of reality. That's the reason why I'm more on the wave side. I said later, and just say that my view is that, of course, we need bits, we need particles, but we need bits and particles actually to calculate, but so to make planes, to do things, to make it useful in a way, to be able to perceive things in a limited way. So particles basically are the expression of those limitations, but deep inside, reality is not like that. It goes beyond that. It's even more than that. And now my argument about these, the second point I wanted to make, it's about just the second point, what you said at the beginning, because I didn't forget, I kept it in behind my mind.
Mm-hmm.
When you are talking about quantum computers,
yes,
and this idea of superposition, of course, using the quantum superposition,
mm-hmm.
isn't it a way to go beyond, aside from the power of calculations and all that, to go
speed?
To not only speed. That's where I wanted to make a little point here. To go beyond the binary way a computer, sees the world, if we can say see the world, even things like, then to be not it's right or wrong, it's plus or minus, it goes beyond that with like a third way, like the superposition is like a synthesis, is something that's neither right nor left, but something else. Like if we were getting closer to these intensities, contrast that goes a little bit on one side, a little bit on the other side, but it's not like it's more a question of intensity, of tendencies, than just a question of it's right, it's left, like being it's like if the reasoning of a regular computer was discrete reasoning, while the reasoning, if we can put it this way, of a quantum computer was more of a non-discrete reasoning.